In this class, we will turn our attention to multiple regression, in which two or more independent variables are used to predict scores on a single criterion. In multiple regression, a set of predictors, or two or more predictors, are used to predict scores on the criterion. Frequently, researchers will call this set or collection of predictors a model, or a model of prediction. In multiple regression, we will be able to evaluate the effect of multiple predictors on the criterion simultaneously. In addition, we will be able to evaluate the unique effect of a single predictor on the criterion after controlling for the effect of the other predictors in the model. For example, we could use multiple regression to determine if scores on a measure of life satisfaction can be predicted by combining information from scores on predictors such as intimacy, income, and anxiety. In addition, multiple regression can be used to determine the unique predictive effect of intimacy on life satisfaction after controlling for the effect of income and anxiety. The regression equation in multiple regression is similar to bivariate regression, except for the introduction or the addition of more predictors. The y-hat is the predicted score on the criterion based upon a participant's scores on each of the predictors. The regression line connects all possible predicted values of y based upon scores on x. A, once again, is the y-intercept, or the constant of the equation. It equals the predicted score of y when the value of each predictor is 0. As mentioned in classes on bivariate regression, when b equals 0 for all predictors, a will equal the mean of the criterion, or the mean of y. Thus, when none of the predictors in the model predict the criterion, the mean of y is the best predictor of scores on y. In multiple regression, the name of b changes from the regression coefficient to the partial regression coefficient. The name is changed because b is computed only after the effects of the other predictors in the model are partialed or removed. Thus, b in multiple regression is based upon the unique ability of its predictor to predict the criterion after controlling the effects of the other predictors. Let's look at this way of looking at b with the help of an example. In this example, we represent a model in which three predictors are used to predict the variance in one criterion. Let's assume that the criterion y is a measure of life satisfaction, and for the predictors that intimacy is x1, income is x2, and anxiety is x3. Notice that each predictor overlaps with the criterion or makes some level of contribution to the prediction of variance in the criterion. However, notice that each predictor is also correlated with other predictors, and thus they also predict variance in other predictors. Notice that part of the overlap of x2 with y is unique to x2, and here it is marked with a U in this example. Also, part of the overlap of x2 with y is shared with x1 and with x3. The value of b in the final regression equation for x2 depends on the unique area in y that's predicted only by x2. The variance in y that is predicted by more than one predictor is redundantly explained and is not accounted for in the computation of the partial regression coefficient for that variable. If x2 had been the only predictor of y in bivariate regression, the regression coefficient b would consider the entire overlap of the predictor with the criterion. Thus, the partial regression coefficient for any predictor in multiple regression will be equal to or smaller than the b for that predictor in a bivariate regression with the criterion. Let's continue with this example on the next slide. Now, let's continue to use this example to talk about additional important issues involved in the prediction of the criterion by multiple independent variables. Note that the size of the unique area predicted by each of the variables depends on the other predictors in the equation. If x3 was removed from the equation, the unique contribution of x2 to the prediction of y would suddenly increase. As a result, b for x2 would increase. If other variables were added as predictors, say x4 and x5, the unique contribution of the predictors we are looking at right now would need to change to accommodate their presence in the model. Thus, the value of b and the unique ability of any predictor to predict scores in the equation depends on the other predictors that were chosen to be part of the model. In general, researchers are best advised to select predictors that add unique rather than redundant information about y. Let's consider another important property of b, or the partial regression coefficient in multiple regression. b can be found to be equal to the change in the predicted value of y when the value of its predictor increases by 1 unit and the value of all other predictors is held constant. Continuing with our example of predicting variance in life satisfaction by using our 3 predictors, let's say our regression equation turned out to be y hat equal to 1.3 times someone's score in intimacy plus 0.09 times someone's income plus a negative 0.25 times someone's score on anxiety plus the constant, which here is 10.50. If a participant in our study had an intimacy score of 17, an income of $50,000, and an anxiety score of 50, the predicted score on y would be 24.6. Before turning to the next slide, see if you can answer this question. If the intimacy score increased to 18, while income and anxiety were constrained to the same values, how would our predicted score on life satisfaction change? The answer is the predicted score on y would now be 25.9. Thus, the predicted score on y would increase by 1.3 raw score units, or the value of b for that predictor. If the coefficient had been negative, the predicted score of y would decrease by 1.3 raw score units.